So we're now in the third part of the solubility topic. So if we try to keep track of where we come from, we start with the idea that some substances are soluble, some are insoluble, and used our periodic table to help us work out which was which. We then looked at solubility as a definition to tell us that some substances are more soluble than other because we give a value of solubility as the amount you can dissolve in 100 grams of water at a particular temperature. The key thing we emphasised at that definition was we have to quote the temperature because the solubility is going to depend on the temperature of the water, and that's where we're going to build on in this wee section, the effective temperature on solubility values. Now what we start with is a wee sentence which you should be quite familiar with. You are already aware of the effective temperature that it can have in solubility. What we mean by that is it's easier to dissolve sugar in a hot cup of tea than a cold glass of water. So for most solid substances, you're going to find it easier to dissolve the substance in hot liquid than cold liquid. And it's not just that it's easier to dissolve, you'll actually be able to dissolve more substance if it's a solid in a hot liquid than a cold liquid. The effect of temperature on solubility is different for different substances. So whilst I just said that generally most solids you find it easier to dissolve in hotter liquids, the trend's going to be slightly different for each solid. They don't all behave exactly the same. The way you're going to be able to see what particular trend is for a solid is by showing the effective temperature in a solubility curve. A solubility curve is just a graph. It's a graph of solubility figures against temperature. So here's an example here for a solid. We've got the solubility values, so grams per 100 grams of water on the y-axis. We've got temperature on the x-axis. Now, it's not that complicated graph, but it can kind of throw people off a wee bit because it seems a bit strange talking about a curve when before we're looking at just individual values. What we basically mean, if I can do a wee sketch at the top, if I even just looked at two different examples, let's say I've got a beaker with 100 grams of water at the start and one beside it. So they both got 100 grams of water, as we expect for solubility. Let's say they got different temperatures though. Let's say this one on the left is at 20 degrees C. And let's say the one on the right is slightly hotter, it's at 50 degrees C. What I'm saying is here, because they've got two different temperatures, I'm expecting I'll be able to dissolve different amounts of solid in it. For example, the one at 20 degrees C, for the particular solid, I might only be able to dissolve 10 grams of the solid in it. However, once I get to a hotter 100 grams of water, I might be able to dissolve 40 grams per 100 grams of water. If I plot that on the graph, so let's say I've got a temperature scale on the x-axis and solubility on the y-axis. So for 20 degrees C, I was able to dissolve 10. For 50 degrees C, I was able to dissolve 40. So what you can kind of maybe get a sense of, I could plot out a nice graph if I got more than 2 points. So I might get some intermediate values, and that will allow me to plot a curve. It might be a straight line, it might be a curve, but it'll allow me to plot a graph anyway. So that's how we end up with this kind of smooth looking curve here. This will have come from doing lots of experiments to work out what the solubility is at particular temperatures, and then just plotting a curve or a straight line through those points. So that's where that graph comes from. It's just solubility against the temperature of the water. One key thing in general to understand is we've got a general curve for solids. Now, I said it might be a curve, might be a straight line. The important thing is that the solubility always increases, as explained here. The solubility of a solid increases as the temperature increases. That's the first key point you need to remember. We'll come back to these 2 points about above or below the line. One wee question maybe could come up in the exam: why does the temperature axis only run from 0 to 100 degrees C? You spot here in every solubility curve, it's only from 0 to 100. Shouldn't be too hard to work that out. It's to do with water. If I go below 0, I've actually got ice rather than water, and it's quite hard to dissolve things in ice. If I go above 100, I've got steam, and again, it's a gas, quite hard to dissolve something in steam. So the reason it's between 0 and 100 is that 0 degrees C is the melting point, or the freezing point, depending on your direction. And 100 degrees C is the boiling point. And we're talking about of water here. So it doesn't make sense to go beyond those melting points and boiling points. So the graph is the graph, but you can do a wee bit of interpretation with it, as we'll look at in the subsequent pages. One thing in general though, we've got this idea of the area above the curve and the area below the curve and what that means. These two sentences here explain that. Each point on or above the curve represents a saturated solution at that temperature. Each point below the curve represents an unsaturated solution at that temperature. Now, that can be quite hard to get in your head unless we look at one example. If I just pick a random point here, let's say this point, and let's just give it a random temperature, it's roughly halfway along. Let's say that point refers to 50 degrees C. Okay. On this axis, let's say it gives me a solubility value. Let's pick a nice easy number. Let's give it 30 grams of that solid per 100 grams of water. Okay, so what this telling me is at 50 degrees C, 100 grams of water can dissolve 30 grams of this particular solid. So that's what's on the line. If I have a point above the line at 50 degrees C, let's say that refers to a slightly higher value, 50 grams of the solid per 100 grams of water. That's saying that this solution is now more than saturated. It's now containing more solid that can possibly be dissolved because I've exceeded that 30 grams it can hold at that temperature. If I go below, if I go down to this point, let's say that's a wee bit lower, let's say it's 20 grams of the solid per 100 grams. At 50 degrees C, 20 grams isn't the maximum amount that water can take. It can take up to 30. Therefore, it's not saturated. To make it a bit more general, what we basically mean is if we've got a point above that line, it's describing something that contains more solid that can be possibly dissolved. If it's below the line, it does not contain as much solid that can be dissolved. So in more general terms, everything above the line of the curve, we would say is saturated. Everything below the line of the curve is not saturated or unsaturated. So that's what that wee point means. It's not particularly important, but just so you understand what those 2 points in your notes are saying. So we've got the curve. We hopefully kind of know what's showing us. How can we use it? So we've got a couple examples here. Here we've got a graph. This is a real life accurate graph for potassium nitrate, so a solid. So we see the curve, it goes up, it is kind of a curve rather than a straight line. It says a solution contains 10 grams of potassium nitrate in 100 grams of water at 40 degrees C. Use the graph to determine how much must be added to make a saturated solution. So we've got a wee bit of information here. It tells us that we're at 40 degrees C, that's our temperature. So along this curve, there's only actually one point which is important, which is the 40 degrees C kind of point on the axis. At 40 degrees C, my curve tells me that if I extrapolate across, again, it's not a perfect graph, doesn't give me a proper scale. I would say that at 40 degrees C, my solubility figure, which is on this y-axis, is, I'd say, 14 grams per 100 grams of water. So that's why I'm using the curve to tell me what the solubility figure is for any temperature I want. The temperature I want is 40 degrees C, therefore it's 14 grams at that temperature. The solution it tells me about contains 10 grams of potassium nitrate and 100 grams of water. So it's asking me, first of all, is that saturated? And therefore, if it's not saturated, how much do I need to add to make it saturated? If I've got a solution that contains 10 grams or 100 grams of water at 40 degrees C, clearly it's not containing the maximum amount it possibly can. It can hold 14 grams in solution. I've only got 10 grams in solution. To answer the question, how much do I need to add? It's basically a case of subtracting. I therefore need to add, so 14 minus 10, so I need to add 4 grams of potassium nitrate, KNO3, to make a saturated solution. Okay, we're going to extend that even more with a few more examples. So we go on to page 7. Now, what we have at the top here, we've got we have a wee appreciation of the solubility patterns for gases. I actually think it's that relevant that for now I'm going to come back to that. More interested in this kind of question section at the bottom. So we've been more practice of interpreting solubility curves for particular substances. So this graph looks very complicated. It's just kind of saved in space. It's the solubility curves for lots of substances on one wee graph, and they're all labelled their individual lines. So it's just lots of lines overlapping with each other. It's nothing more complicated than that. So again, I probably would say you can have a go at these. There's nothing too kind of mind-blowing here. It's just kind of reading the graph, interpreting it. So maybe pause the video, have a go first. But I'm going to go through the answers now with you. So there's 5 parts to look at. Part A, simple enough. Which solid is most soluble at 10 degrees C? Going to look at my temperature scale, go to 10. look up, find the line I get to which is highest for 10. It's actually this one here, NaNO3. Notice it's not the highest at all temperatures, but at 10 it is definitely the highest. Therefore, the answer to part A is just NaNO3. Part B, at what temperature do KCl and NaCl have the same solubility? So again, we bit of graph work. Here's my KCl line. Here is my NaCl line. Now it's a wee bit hard to see in black and white. At the point where I have the same solubility is going to be where the lines overlap. So if I look carefully, again, it's hard to say exactly. I'd say it's pretty much at 30 degrees C, the two lines cross over. Part C. What's different in the solubility trends of NaCl and KNO3? So again, look carefully. Here's KNO3, this line here. KCl is this line here. So it's touching on something I may have mentioned in passing earlier. Whilst for solids, all of them, their solubility will increase as you heat it up, the actual shape of the trend is going to be a wee bit different depending on each solid. Some of them might be straight lines, some of them might be curves. What we see for KNO3 is actually a curved relationship. It's not linear. But KCl is a completely straight line. It's a linear relationship. So I would say for C, KCl is a straight line. I could say it's linear, but straight line relationship. And for KNO3, it's a curved relationship. So it just depends on the solid. There's no way of predicting that. You just have to kind of interpret it in a graph. Part D. At what temperature would 6 grams of K2Cr2O7, that's potassium dichromate is the name of that. At what temperature would 6 grams of it saturate 10 grams of water? So there's a wee bit of work to do here. So I have to work out 6 grams saturating 10 grams of water. Now I have to be careful here. 10 grams of water is not what's on this graph. It's the standard value of solubility, which is 100 grams of water. What the question therefore is basically asking is, what temperature would 6 grams saturate 10 grams, which means at what temperature would 60 grams of the solid saturate 100 grams? So again, scaling up, times it by 10, it's 60 out of 100 grams of water. So now I need to look at my graph. This is the curve for K2Cr2O7. I'm looking for the solubility for 60 grams or 100 grams, which is here. It's going to mark a wee point here. If I look down to my temperature scale, again, it's not a perfect graph, it's kind of like a wee rough one. I'm looking for the temperature at which that is the solubility value. Because remember, if it's saying what temperature will saturate it, solubility is the temperature at which it's saturated. So 60 grams per 100 grams will be the saturating amount at just over 80 degrees C. I'm going to say 82. Again, it's not a great graph, but we'll say 82 degrees C. Part E, a mixture contains 20 grams of KCl and 50 grams of water at 80 degrees C. Is the solution saturated? So, it's a similar looking question because I'm given values for a salt dissolved in water, but it's not the standard solubility figures. I've got 20 grams of KCl and 50 grams of water. That's not perfect. I want it in 100 grams of water. So I'm going to do a wee kind of conversion here. So 20 grams per 50 grams of water. It's basically asking about having 40 grams in 100 grams of water. And the question now is this saturated? But again, it's a specific temperature. It's 80 degrees C. So if I look at 80 degrees C, and if I look for KCl, I'll find a value here. At 80 degrees C, the solubility value of KCl, again, if I look across, it's just over 50. I'd say it's 51 grams per 100 grams of H2O. So at 80 degrees C, 100 grams of water can hold and dissolve 51 grams of KCl. The solution I've got is the equivalent of 40 grams per 100 grams. And that tells me that that particular solution isn't actually saturated. It could hold a wee bit more KCl. So therefore, is not saturated. So there's a few examples of questions which involve interpreting solubility curves. Similar kind of questions, just trying to work out, are things saturated or not saturated? The only difference is you're getting the information from a curve, not from just information given in a sentence. The last thing to look at on this page, to be fair, it's not something that comes up very often in exams, but it is on your spec. It's solubility curves for gases. Most of the things in this course are on solids, but you can analyse gases a wee bit. Now, first thing just get in your head is the idea that gases do indeed dissolve. It's maybe not something you think about that much or that familiar with, but they do. There are actually two kind of everyday kind of phenomenon you can think about which do prove to you that gases do dissolve in water. First thing is fizzy drinks. The gas that makes fizzy drinks fizzy is actually carbon dioxide. So whenever you look at a fizzy drink just sitting on a table, it doesn't look like anything's happening. You see a coloured liquid. However, when you shake it, suddenly, as if from nowhere, you've got lots of bubbles of gas whenever you open it. The gas is coming from the liquid. What you've dissolved in that fizzy drink is lots of carbon dioxide. And when you shake it, you kind of agitate it. It allows some of the gas to actually come out of the liquid and back into the air. So whenever you shake a fizzy drink, what you're basically seeing is dissolved carbon dioxide escapes the liquid. Escapes the water, sorry, more exactly. So it's dissolved to make it fizzy. When you shake it or agitate it, the gas comes out. The second thing to think about is fish. Fish obviously spend their whole lives underwater, but they're quite happy and they live healthily underwater. Which raises the question, most organisms need oxygen to live. Where does the oxygen come from? If you've never thought about that, fish have got gills. Gills work by passing water through them and are able to absorb oxygen from the water. That will only work if you've actually got oxygen in water. And again, you might not have thought before, but seawater and any water does actually contain a fair bit of dissolved oxygen, which fish can use. So fish survive underwater because oxygen is dissolved in water, which they can directly breathe through their gills. So just accept that fact that gases do actually dissolve in water. And there's only actually one other main point beyond that. Again, gases aren't a major part of this topic. It's the shape of their solubility curve. So remember, solubility curve is just describing the solubility for different temperatures. What you might notice by looking at the graph on page 7 is that the curve's the other way around. What we find for gases is, as the water gets hotter, the gases become less soluble. So to make that clear, that's the opposite trend for solids. All solids become more soluble as the water heats up. Gases become less soluble. This is a different effect. So see in this curve, the solubility is decreasing as the temperature increases. So that's just a wee point to learn for your exam. The solubility is decreasing. One interesting kind of reason that's important is this idea of thermal pollution. Might sound a wee bit strange talking about thermal pollution. It's basically implying that heat is causing damage to an environment. It's very common in the areas around factories. Now, factories produce a lot of heat. The way they keep that under control is to use what's called a coolant, obviously to cool it down. The most common coolant they'll use in factories is actually seawater. Lots of factories are built next to rivers or next to the sea. They'll suck the water in, which is obviously reasonably cold. It'll cool the factory down, and they're going to pump the wastewater back into the river or into the sea, slightly heated up. So they've not actually added any chemicals to it. It's not like damaged environmentally. It's just slightly hotter because it's been used to cool down the factory. So you might think there's nothing actually very much wrong with that. It's not kind of being tainted by chemicals. However, it does cause a bit of an issue for fish living in the area because the water they're swimming through now is slightly warmer. The effect of slightly warmer water is on a gas that's dissolved is that less gas can dissolve. The important gas for fish is obviously oxygen, and if they're now swimming in slightly warmer water, there's now less oxygen dissolved. If there's less oxygen dissolved, there's less oxygen available for them to sustain themselves and keep alive, which leads to a lot of fish actually dying. So thermal pollution is the idea that when you heat up water, hot water holds less dissolved gas. Therefore, if you heat up, most commonly the sea, if sea heats up, there's less oxygen for fish to use. And therefore, fish can die, which is very unfortunate. So that's the only kind of thing you need to know about gases. Solubility decreases, temperature increases, leads to something called thermal pollution caused by factories heating up the water around them.